Dr. Robert Garrison received his PhD in astronomy from the University of Chicago in 1966, 30 years ago. After serving a couple of years with Mount Wilson and Palomar observatories, he joined the faculty of the University of Toronto, where he's now a professor of astronomy and an associate director of David Dunlap Observatory, in charge of the 60-centimeter Helen Sawyer Hogg telescope at U of T's Southern Observatory in Chile. He's served on the Council of the Canadian Astronomical Society and has now moved on up the ladder to become the second Vice President of Canada's Senior Astronomical Society, the RASC. He's a member of several international astronomical organizations and has served as the President of the IAU Commission on Stellar Classification. Dr. Garrison's been a member of the RASC for 28 years and is an avid promoter of astronomy to the public and an advocate of amateur and professional cooperation in research. He has an extensive publication history and gives many public interviews, lectures, and presentations. I think his role in the popularization of astronomy is very important, and it gives me great pleasure to present it tonight. Dr. Garrison.
Well, we from the suburbs out in Toronto suburbs of Ottawa, that is, don't get into Ottawa very often these days since the Hertzberg Institute has moved out west. But this week, this is the second time I've been to Ottawa. So the first time was on Monday night when I was invited to the state dinner for the President of Chile. And it was a grand affair. First time I'd rented a tux since high school, which for me was a long time ago, I'll tell you. But it's always fun to come back to Ottawa. I've always enjoyed it. I brought a 10-hour talk along with me because you're all astronomers, or at least, no, half of you are astronomers. And you could stay up all night, so there's no problem there. But I guess because of the spouses that came along, I won't give the 10-hour version. I'll shorten it. Actually, it's been getting shorter and shorter ever since the business meeting began. But but I'd like to cover a number of grounds today. And when you have a mixed audience like this, all the way from people who are physicists or astronomers, and all the way to people who couldn't care less about astronomy, just were dragged in by their spouse. When you have a mixed audience, it helps to have a two-tiered talk. So that's what I'm aiming at tonight. On the one hand, I'll say some things that will be meaningful to the astronomers in the crowd, and at the same time I'll show some pictures so that you can enjoy the pictures if you can't understand what's going on. I'd like to cover a number of items tonight, and one is a sort of a philosophical talk about what it means to do astronomy and why you need a balance in astronomy and not just monster telescopes. Astronomy is not like physics. It's a different subject, as you all know. The second thing I'd like to do is to give you a bit of a travelogue to show you what's going on in Chile with our little telescope there, and use that as an example of how small science or small telescopes, now 24-inch or a 60-centimeter telescope is a big telescope for an amateur, but it's a small telescope, almost negligible for a professional. So we have to struggle to keep it alive. So I'm going to use that as an example of what can be done with a properly equipped small telescope. And you don't have to have the biggest monster to do frontier science. And also then I'm going to talk a little bit about some of the science that we've done. So that's a big order, and I'll try to get as much as I can in, and I may skip over some slides, especially because I can't change the order of them like I can change the order of the overheads. This is the 25th anniversary of our telescope in Chile as well. So I didn't realize that it was your 25th as well, but 25 years ago in August, we had first light for the telescope in Chile. First time any photons got through the telescope. That was an exciting time, but when you're on the mountain, on a mountain in the middle of the desert, 180 kilometers from the nearest town, you have problems. And if you have problems getting the telescope going, it's not so easy to solve them as it is if it's in half an hour's drive from Ottawa. Why did we put a telescope down in Chile after all? Well, Sidney Vandenberg and Rene Racine and I had all been down to Chile to Cerro Tololo, the American observatory, to observe. And we were just so taken with the southern skies. They're magnificent. If you've never been to the south, you surely must someday put in a trip to the southern hemisphere just to look at the southern sky. It's an absolutely magnificent sight. There are more bright stars in the south than there are in the north. In fact, the dividing line between for equal numbers of stars in the north and the south is minus 20 degrees. And that's it's a small area in the south that's south of minus 20 degrees and a large area that's north of minus 20 degrees. So that's a significant change. In fact, on a moonless night that's clear, you can see quite well. You don't need a flashlight, you don't need anything of the sort. There are lots of other reasons. We at the David Dunlap Observatory struggle along with lighting, and it isn't always successful. There's a letter here from somebody from the city council or something. They say they can't understand why our looking at the same old star should interfere with a shopping mall promotion. So I'm sure Rob Dick will appreciate that sentiment. But in Toronto, there's certainly a lot of things we can do. In fact, a lot of things that we have done. And what we've done is concentrate on high dispersion spectroscopy. And we're perfectly able to do that. The city lights don't bother us a bit. The clouds don't bother us a lot. So it's an area of astronomy that we can excel in Toronto. But that's not my specialty. And it wasn't Sidney Vandenberg's specialty, and it wasn't Rene Racine's specialty. So we were more interested in going to where we could get good skies, good dark skies, very small, tiny images, because there's very little turbulence in Chile. So that's basically why we went down there. But as I say, it's been a struggle to keep the place going over the years in the wake of the large telescopes that have been built in Canada and outside of Canada, and in Hawaii, for example, and one which is to be built, and that's the Gemini, which Canada has a 15% share in. But those telescopes are so big, and they're wonderful, and they're so expensive, that in order to pay for them, what we've done is pull the money out of everything else. And that's a mistake, because really what you need is a balance in astronomy as in those other subjects. And as I say, astronomy is not like physics. In physics, and there are more and more physicists that are coming into astronomy with the attitude of physics, and that's what we have to be aware of. In physics, if you have an accelerator, you create a particle, and you bombard particles, and you observe particles, and a certain size accelerator is needed to observe a certain particle. But all the particles in the universe of that type are the same. So you've seen one particle, you've seen them all. And once they've done that experiment, then they throw that accelerator away. Maybe it costs billions of dollars, but they throw it away, and they have to build the next bigger version. And so that's the physicist's attitude towards advancement in technology. In astronomy, however, it's not the same. Once you've observed a star, not only does that star change, but another star is not like that star. Even another star of the same type is not often, very often like that star. So it's a slightly different emphasis in astronomy. And for that reason, we'd have to keep struggling to keep alive this small telescope, because after all, if you don't have a big telescope, you're not doing real science, according to some people. So I'd like to, I guess I really don't have time to go into details on this, but big science versus little science, whoops. In Canada, can we afford it, and can we afford not to do it? And that's really what the question boils down to. We are partners in Gemini. Gemini is 2 8-meter telescopes, one in Chile, one in Hawaii. And 15% of that costs us something like $15 million for the, oh no, that's, I'm sorry. Canada shares $30 million here in Gemini. And in order to pay for that, the government said that has to be a zero-sum game. In other words, we have to pay for that $15 million out of all of the rest of astronomy. So that means small telescopes have to go, other kinds of research have to go, so on. Is it worth it? On the other hand, there's certain kinds of astronomy that you can't do without an 8-meter telescope. So yes, it's probably worth it, but it is a struggle, and it doesn't cost much to keep a small telescope alive. And that's where we've made a mistake, is to try to kill everything else except the big telescope. There are a number of arguments for that, and I really don't have too much time to go into it. But let's look down at the bottom here. Cost comparisons with small science. The University of Toronto Southern Observatory, for example, is a very productive little telescope. And the reason it's productive is not because it's a big telescope, but because it's in a dark sky, a completely dark sky, and because it has very low turbulence, so that the images are tiny as they are anywhere else on Earth. So it turns out that the interesting comparison is that at the University of Toronto Southern Observatory, the cost per produced paper, per published paper, is about $4,000. The cost per published paper with Canada, France, Hawaii telescope is about $60,000. It'll be over $100,000 with the Gemini. And that's expensive. The cost, in fact, the cost of a telescope goes basically as the 2.6 power of the aperture, but the light gathering power only goes as the square of the aperture for direct images, and only as the first power of the aperture for spectroscopy. So you're paying a lot to get a little more. And that even gets worse because sky background limit inhibits the power at the faint end, so the gain is less than the square. Basically, the argument that I wanted to present is simply that we need to balance large telescopes and small telescopes. So the University of Toronto telescope in Chile is small in professional terms, but it's very large in terms of results, mainly because of the philosophy that we use in giving it time. If you have a big telescope, there's so much demand for the time on it that in fact what you do is a professional astronomer may get 3 or 4 nights a year on a large telescope. Well, the first night's cloudy, second night the instrument doesn't work, and the third night you begin to roll. Well, with our telescope in Chile, our runs are generally 2 weeks. So yes, you have the same problems you do for the first couple of nights with a big telescope, but then you get on a roll and you start producing some real interesting results. And you can produce take a lot of data in 2 weeks. Also, we base a lot of our approach on experience and schemes and large surveys. We can do large surveys. We can take a month or 6 months or 6 years on the telescope, and we can do large surveys. And in fact, two of the most productive things we're doing at the present time are large surveys. We are about 97% complete on a project to observe the 10,000 brightest galaxies in the southern hemisphere. We're 97% complete on that, and that's taken us about 6 or 7 years to do, but that's all part of a NASA extragalactic database, which is used by all astronomers in the world and can be accessed from the web. So this is a tremendous survey, which will be very productive, but something which you cannot do with a large telescope. And discoveries are important. And for real discovery, you really need a large interface between good science and reality, i.e. between observation and experiment. And in order to do that, you have to have time on the telescope. And if you have only one astronomer on one large telescope, that's not much of an interface with the real world. So your chances of discovery are much reduced. Also, so on the basis of that, for real discovery of new phenomena, it follows that it's probably better to fund many good scientists at a modest level than just a few good projects as they do in the US. In fact, the Canadian model, for the NSERC model for funding in astronomy is one of the best in the world. And I find that it's, philosophically, it's just great. The only problem with it is that there's not enough money in the pool. If Canada were able to put more of its money, research money, into the pot, we would have probably the best research organization in the world. Curiosity drives better science than strategy alone. Discovery is outside of normal expectations, almost by definition. If it's a discovery, it's not normal. And so, hence curiosity is part of discovery. But then for the follow-up, strategy is necessary and important. And indeed, it's very difficult to discover things if you only have a few nights a year on a telescope. So if we remove curiosity, it's very difficult if you have a few nights of the year to follow up on anything that you discover out of curiosity. And what drives a good scientist is pure curiosity. And actually, amateurs are way ahead there because they often have their own telescopes, or usually have their own telescopes. So if they find something curious and interesting, they can follow up on it. Professionals often don't have that luxury, although if there's something really spectacular that they discover, of course, they can follow up on it. Well, one of the problems we have with funding is that is the market. The basic science is long beyond the timeline of the market economy. And if you think about it, the basic science discoveries are often made decades or even centuries before they're useful, or before anybody discovers how to make them useful. The story that comes to mind immediately is that of Faraday. Faraday discovered electricity and had no idea what it would be useful for. And in fact, if we would have more funding in astronomy if we could convince the bus drivers that their job depends on the discovery of electricity a century ago. And that's the job that we popularizers of science have to do. We have to convince the man on the street or the woman on the street that in many ways their lives depend on the discovery of basic science, maybe quite some time ago. And that's much, the market system invests for a relatively short-run return. If you went to a board of directors of a company, they'd say, well, what can you give us in a few years? Or 1 or 2 or 3 years, and then they'd expect some return there. So basic science is like the arts in that way. We have in the arts, you can't argue that there's going to be a definite return after this concert or that concert, but the general cultural level will be raised over years. And in fact, that's the kind of thing that basic science has to deal with as well. The general level of basic science, if it's increased, will increase our general well-being, just as increasing the arts will increase our cultural heritage. So even the government, in fact, we had an interesting case here when we were going to build the large telescope in Chile. We went to the provincial government. This was some years ago, about 10 years ago, and we said, we would like to establish a center of excellence and build a big telescope. They said, well, how long will it take to get some results? And we said, well, it'll take 5 years to build the telescope. And then we'll have to do some observing, so it would be maybe 10 years before we get some results. Oh no, we have to have publishable results and spectacular results in 5 years, because that's when the next election is going to be. So even governments are driven by that, by a shorter time scale than we can afford in astronomy, than we can produce in astronomy. We can't always produce the spectacular results on a short time scale. Well, for the best results then, you really have to increase the number of high-quality scientists and give them just adequate support to carry out good experiments and observations. But you should keep in mind that not all discoveries are spectacular. Not everything, I mean, discovery doesn't mean that just the discovery of the brightest supernova since 1604. That makes the cover of Time magazine, that's true. But that's not the only way that science proceeds. In fact, science moves ahead by the hard work of a large group of dedicated, aware, creative scientists, not just a lucky few who happen to be in the right place at the right time. And I'm reminded of Newton's statement that he thought he stood on the shoulders of giants. Yes, he made a big advance, but there was an upward pressure of discovery before that to enable him to make that advance. And he was a person of special insight. But without the previous research and contributions, he wouldn't have made his contribution. Well, what are some of the advantages of small telescopes over big telescopes? I've hinted at some of them. Adequacy. You don't need to sledgehammer when a gentle touch will do the job. The Imager CCD that we have in Chile with a UBVRI photometry can be used to observe the brightest billion stars. It's a lot of stars, you know. Why do you need a big telescope to observe any of those brightest billion stars? You don't. The CCD spectrograph can reach the brightest million at a slightly less than 1 angstrom per pixel resolution. Well, that's an incredible number of stars that you can get a lot of interesting and important information on. So use people and ideas instead of brute force. I mean, a big telescope is a brute force way of approaching it, but you don't need to. Availability. You can build, for example, for the cost of one Keck telescope, you could have built something like 100 2-meter telescopes. And if you put 100 scientists to work on 100 2-meter telescopes, my claim is that you would have more discoveries than you will from one scientist working with a 10-meter telescope. Now, there's some things you can't do with a 2-meter telescope that you can do with a 10-meter telescope, so the argument falls apart at that point. Flexibility of scheduling and instrument changes. It's awfully easy to take a photometer off and put a spectrograph in its place on a small telescope. With a big telescope where the spectrograph weighs 1.5 tons, it's not easy to take it off and put it on during the night. Serendipity and speculation. You have more freedom to follow up on innovative research leads, not so much pressure to produce a predicted result from one night's observations. The pressure is real, and the high pressure is so high to produce that, in fact, in making a proposal for large telescope time, you almost have to predict exactly what you're going to discover. So, in fact, that's confirmation, not discovery. Wide-angle work. At the University of Toronto Southern Observatory, we have a 22 second per millimeter, and that's great for galaxy survey. It turns out that we can get most of our galaxies into the scheme we want to get them into. We can monitor interesting objects, bright objects for variability and so forth. We can observe standards. The incredible thing is that Hubble Space Telescope, for example, the Hubble Space Telescope has no neutral density filters, so they cannot observe any stars brighter than 11th magnitude. Most of the standards that we've observed over the last 20 or 30 or 50 years are brighter than 11th magnitude. So there's almost no way of calibrating the Hubble Space Telescope observations. In addition, time is so valuable on large telescopes that you don't take the time to calibrate the observations properly. So the observations with a large telescope are often inferior to those with a small telescope, well calibrated. So that's another thing. Basically, we're using first-class telescopes, large, expensive ones, to obtain poorly calibrated data, which is crazy. Well, actually, I'm going to skip some things here. I'd like to just support one of the statements I made was that the University of Toronto Small Telescope in Chile is enormously productive. Here's the number of publications per year from 1987 to 1993. And about in here, we put in a CCD, so it took a couple of years before the publications started coming out. But you'll notice what happened. So we're leveled off at about 30 publications per year. Now that's an enormous amount for a small telescope at the cost of the support of a small telescope. And compared with the number of publications with the big telescopes, it compares very favorably. Well, I don't have time to go through in detail all of the kinds of discoveries we made and so forth, but I'd like to, just let me pick out a few highlights. We actually observed a supernova back in 1972. It was the brightest in a century. And we observed it actually in an interesting way. It had been discovered by George Herbig, using the 120-inch Lick Observatory. Now, Lick Observatory with 120 inch is much better than us with a 24-inch telescope. So we thought, in fact, everybody in the world thought, well, George Herbig, who is the world's best spectroscopist, is just banging away at that and gathering all the glory, and we don't need to do it. But I actually took spectra of this supernova because I thought, well, illustrations of this spectrum evolving would be interesting for an elementary class. I didn't think, I thought also that George Herbig was really doing it properly, and that he would do it much better than I would. But in fact, that was his last night on the telescope, and he didn't have the telescope for the next week, and they didn't give it to him. So in fact, for that next week, the spectra were not taken of that supernova, and we have some of the only spectra taken of that supernova. In '73, we discovered a pure helium star with the telescope, and that's, in fact, the purest helium star of its class. There's just nothing like it in the sky, and that was discovered with that little telescope, only 2 years after its dedication. There's lots of other things here. Down further, we get to supernova Shelton 1987A. I'll show you some slides of some pictures of that in a bit. Ian Shelton is now Dr. Shelton as of September. He's got his degree in astronomy now. And he got it because he discovered the supernova. So all you have to do to get a PhD in astronomy, or get at least an entry into the University of Toronto Graduate School in Astronomy, is to discover the brightest supernova in 400 years. Well, he had terrible grades before that. So, well, no, seriously, we couldn't allow him in graduate school, and so he put in 4 years on the telescope down there as a resident, and after he finished that, after he discovered the supernova in his 4th year, I asked him a couple of months later. I said, "Well, okay, now that you're famous, Ian, what do you want to do with your life?" He said, "Well, Bob, I really want to go back to school and go to graduate school." But I said, "But your grades are C's, C's and D's." And he said, "Well, yeah, I know." But I discovered, of course, and knew that it was because he was a perfectionist. So he only handed in half of his work. And if you had averaged some zeros and some 100s and 50s, then you get or if you get average hundreds and zeros, you get 50s. So that was why he had poor grades, not because he couldn't do the work, but because he didn't do it. So anyway, I spent the first year counseling him on how to get things in, and it worked. In fact, I had to go to the dean, and I said to the dean of the graduate school, and I said, "Tom, I said, Ian Shelton would like to come here." He said, "Oh, wonderful, wonderful. This guy's the one that discovered the supernova. We need somebody like that in our graduate school." And I said, "Well, there's just a little problem, this transcript doesn't look too good." "Oh, no problem. We have this category we call creative professional achievement." So he was in. Well, anyway, the two ones at the bottom are ongoing projects, and these are very important projects, actually, and they take about 50 nights each a year. But one is the NASA Extragalactic Database Survey of 10,000 Galaxies in the red, and that's now 97% complete. And we also have, we're also one of the network of MACHO follow-ups, and our data for the MACHO project is the best data going, and it showed. Now, I guess I have to backtrack one more step and tell you that MACHO is massive, massive compact halo objects. I don't know what MACHO is, but it's a nice catchy title anyway. And these things are massive objects that are in between us and another star. And they're so massive that they bend the light of the other star and they magnify it as a gravitational lens. It's actually quite a clever idea, and it's been used for several years now. Well, once we joined the network, our data were so good and so well spaced that we were actually able to show that the object that's doing the lensing is in fact a disk and not a point source, which is the theory, of course, is that it's almost a point source, or for all intents and purposes, it's a point source. Anyway, we were able to do that. It's very difficult for any of the other telescopes to have as much of a follow-up because we've got the clear weather. It's clear 85% of the time in Chile, so it's a magnificent place to go. Well, I want to make one more point before I go on to the travelogue. And that is, let me summarize it rather than listing all these people. And that point is this, that these are the resident observers that are in Chile. And now I've got another list all the way back to 1971. But the point is that I want to make to you is that 7 out of 14 of them went on to the PhD. These are the residents who take care of the telescope, who live there full time. They have to do everything. There's no technician they can call on. If the telescope breaks down, they can't go and they can't call the electrician or the electronics person or the computer person and say, come and fix it for us. Which is what we do at the David Dunlap Observatory and what they do at big observatories. Everybody has a specialty. If the telescope breaks down, well, you either call the person and try to have them come up and fix it, or you just close the telescope down and say, fix it the next day, and the technician comes up, fixes it, and then you can observe the next night. But in Chile, that's not the way we do it. We have only one person, and that one person has to do everything. Optics, electronics, computers, observing also. So they learn a lot on the job. And they're generally young people. We only assume they'll be there for a year or two, and they stay there for, as I say, a year or two. And in that year or two, they have to. The learning curve is very, very steep. It takes them about 6 months to learn everything there is to know about the telescope, and then the next 6 months is a little smoother. But look what the results are in terms of training of skilled scientific personnel. 7 of the 14 that we've had over the years have gone on to the PhD and are now PhD astronomers practicing. In fact, most of them are professors at various universities. But the interesting thing is that 3 of the 14 are now optical engineers at the 3 largest telescopes in the world. The Keck, Peter Wazinowicz, went to Arizona, got a PhD in optical sciences, and is now chief optical engineer at the Keck telescope, which is the largest telescope in the world. Rick Salmon, the first University of Toronto resident, went on to Cerro where they snap us up. They snap our residents up quite fast because they're quite valuable already. And then he spent several years there, and then went on to CFHT, where he is now the chief engineer. John Philhaber followed Ian Shelton and was there for a year. He went on to Carnegie and then went on to Columbia University, and he's now the chief optical engineer for the 4-meter telescope in Tolola, the biggest one in the southern hemisphere. So from our little bush league, little tiny telescope, these people have advanced into the field and have turned out to be quite productive. skipping over a lot of stuff here. Okay, now we're ready for the travel log. I think I can't turn this. Oh, it is on, right? Well, we go from Toronto to Chile. It used to be Canadian Pacific had a nice, Canadian Pacific Air had a, I can't go further back than this, so if you want to change seats, I don't know if you can see. CP Air had a beautiful flight, non-stop, Toronto-Santiago, 10 hours. Great flight. Stopped about 4 or 5 years ago. Now they go way east to Sao Paulo, Brazil, and you have to change to a Brazilian airline to go to Chile. It's lousy. It takes 17 hours. But anyway, when you wake up in it's an overnight flight. They're all overnight flights. And when you wake up in the morning, this is what you see, the Andes. And this is Aconcagua, the highest mountain in the Americas, in the Western Hemisphere. It's about 22,000 feet, 80. And these little things here are around 20,000 feet. So once we arrive in Santiago, that's way down off the map here, we drive up the coast, or take a bus up the coast, 7 hours to La Serena, which is about 440 kilometers to the north. And that's a headquarters for all of the observatories. The Cerro Tololo Observatory, the American National Observatory, is here, and the ISO La Silla is right about here, and Las Campanas, where we are, is up here. Now, just to put it in perspective, the ISO annual budget, this is the European Southern Observatory, their annual budget is $30 million. The Cerro Tololo annual budget is about $10 or $15 million. The annual budget for Carnegie, who owns the mountain that we're on and has three other telescopes on the mountain, has an annual budget of about $1.5 million. And of course, the Canadian budget, guess, anybody? 100,000. So that puts it in perspective. But we do keep our heads above water, and we do just as well as anybody. And so this is a close-up of the same, and you can see that as the road goes up here, there are some names of towns here. We're 180 kilometers north of the nearest large town of 50,000 persons. These names, however, are simply stops on a mining railroad that goes up here, a narrow gauge little railroad. Katsuyuya, for example, is 10 houses and a school. Inkawasi was a mining town. It's now a ghost town. So there's really nothing. In fact, the population density up here is 1 person per 100 square kilometers. 1 person per 100 square kilometers. No light pollution. Or any kind of pollution. No car pollution, nothing. It's really a spectacular sight. First time I went up there 25 years ago, I walked up, and somebody had gotten their signals mixed so that the horses were at the top. And if any of you have been with horses and ridden horses anywhere, you know that riding a horse down the mountain is the most excruciatingly painful thing you've ever done in your life. I don't want to ride a horse ever again. Riding the horse down the mountain was hard on the horse and hard on me too. It was fun walking up. This is apparently somebody who was talking to me beforehand said that he remembered this slide from some years ago shown by Sidney Vandenberg. In fact, Sidney has never observed there with our telescope. But Sidney Vandenberg and René Racine and I had all worked for Carnegie for a couple of years before we started this telescope project. Now, Carnegie owns the mountain. Carnegie didn't want us to build a house near the telescope. They said, you don't need it. We're going to build a lodge. We're going to build a magnificent lodge. You don't have to have a house. So and we don't want you to have a house. Well, we said, yeah, but you know, we worked for Carnegie, and we said, how long will it take you to build it? They said 6 months. Translation, 6 years. 6 years later, there was a lodge. So we were right and they were wrong. Anyway, we didn't think that it was a good idea to put up with this for the 6 years we thought we had to wait for Carnegie. So we built ourselves a little house on the mountain. It's a very pleasant place to be with a nice view, as you can see. It's wood paneled, so that just to remind us that there are trees in the world somewhere. Sometimes when you come down to a place like this, it's a little bit barren. It seems a little bit barren. Once you get used to it, it's beautiful, absolutely stunningly beautiful. We try to put a little native art in here too. It's a nice, comfortable place. All of the rest, except for the wood, all of the rest of the house is built from local materials, including the stones from the mountain. We just had a first-class stone cutter come up and split the rocks and put it into the house, and that was it. There's a lot of flora and fauna down there. This is the condor, the Andean condor. It's a huge bird. The largest wingspread that has been seen is 30 feet. This one is probably a tiny one. It's only got about 10 foot wingspread, but it's a magnificent bird. They look like turkeys. They're kind of a vulture, so they're not very pretty. But in the air, they're absolutely magnificent. They can hover for hours. And we feed them. This is not taken with a telephoto lens, by the way. This is straight. I'm standing this close to the thing. They have no fear of people, especially if they feed them. There are other creatures here too. The scorpion, not only in the sky, but in the desert as well. So you learn to pound out your shoes before you put them on in the morning. I've only actually seen a couple in the house in 25 years, so it really isn't a danger, and they're not fatal. In fact, we've also had tarantulas in the house, and they're not fatal either, but they're sure not pleasant to live with. So this is the way the mountain looks. This is the Carnegie 2.5 meter telescope, 100-inch telescope. This is the Carnegie 1 meter telescope, 40-inch telescope. This is the University of Toronto 24-inch telescope, 60 centimeters. And this one here is the one where the supernova was discovered, the actual discovery. With this telescope, we did the first photoelectric observations, but this is where the supernova was discovered. I'll come back to that in a few minutes. There's the little house. Shows the house better with the split rocks right on the walls here, and red tile roof. You can see why we go down there. It's a magnificent sight. I try to take the perspective so that the Canadian Dome looks bigger than the other one, but it doesn't. You can't do that from all angles, obviously. This is a nice angle, taken early in the morning, before sunrise. Whoops. Oh, okay. So this is the kind of sky we go for. It's a very dark sky. Just to familiarize you a little bit, I'm taking it into the night now. You can see an old familiar constellation here, but the difference is that this is Orion. Here's his belt and his sword, the euphemism. Knees, shoulders, head. But he's upside down. This noble hunter with his bear club is upside down, falling out of the sky. So he doesn't look quite so noble in Chile. This is short time exposure. Here's another view of the telescope, and this one I just set up the telescope on a tripod. And I'm a great supporter of Terry, and I think he does a magnificent job of popularizing astronomy. And Terry once expressed the view that he would like to go down there, so I thought this was something that was worthy of the telescope, even though he wanted to do it just to take pictures, pretty pictures. So he and Alan Dyer went down there we gave them 3 nights, and of course Terry, I think, has probably spoken here once or twice, or maybe 10 or 20 times, and has extolled the virtues of the southern skies and the University of Toronto's southern station. But one of the points, one of the reasons we go down there is that the center of the Milky Way galaxy passes directly overhead in Chile. And so you can lie down on the ground and look up into this maw. And it's just so magnificent. It's a sight which you've never seen the likes of before. You certainly don't appreciate what the center of the galaxy looks like from here when it's way down on the southern horizon in the middle of summer. There it falls directly overhead. Well, just to show the supernova, this is the telescope with which the supernova was actually discovered. It's a 10-inch astrograph, and it takes 20-inch plates, big, huge 20-inch plates. And Ian Shelton was the only one that could make it work. In his spare time, when somebody else was using our telescope, Ian is the kind of guy that can't sit around twiddling his thumbs. He always has to be doing something. So Ian was taking the definitive photographs of the Large Magellanic Cloud when he discovered the supernova. In fact, the night of the discovery, he had stopped it down to 5 inches. So it was a 5-inch telescope that discovered the supernova. And in fact, it was the telescope was built in 1905, so it's an old museum piece. So don't throw your telescopes away. They're still going to do some good someday, maybe. Okay, I guess that's the two slides I couldn't get into this slide projector. That's another picture of Ian. He looks a little bit grayer and older now, of course, 10 years later. This is the 10th anniversary, or February will be the 10th anniversary of the discovery of the supernova. This is a photograph, a color photograph, which Ian took a month later, which this photograph is actually a 3-hour exposure, hand-guided. And the images are as tiny as any images you'll ever see from Earth, at least. Here's the supernova. Here's the Tarantula Nebula, which is in the Large Magellanic Cloud. It's a site of massive star formation. It's very massive stars. This nebula is so much bigger than the Orion Nebula, for example, that if this were at the distance of Orion, the whole night sky would be illuminated as brightly as the full moon, as it is under the full moon, just from this nebula alone. This is a huge, huge nebula and a huge cluster of very massive stars. So this is a kind of region where you might expect such things as supernovae to take place. This is a blow-up of that same photograph, and it's really a magnificent picture. You can see the diffraction rings here. You can actually see the images here. The tiniest images are about half a second apart, which is the diffraction. The diffraction limit of this telescope is about 4/10 of a second apart.
That was with the same Bruce telescope?
No, this is taken with our telescope.
Oh.
This is with our. In fact, you can even see the keepers holding the mirror in place. So the seeing on that night must have been magnificent for 3 hours. This is something that you won't see usually. This is a spectrum, a series of spectra taken of the supernova from a couple of nights after its explosion. And you can see, for example, this hydrogen line. This hydrogen line you can see here. Here is where the hydrogen line is supposed to be. This is a standard star. And so the hydrogen line should be here. It's over here. It's at about 18,000 kilometers per second. So the explosion is moving out from the star at 18,000 kilometers per second. It's the most violent explosion in the universe. And in fact, even down here, it's over 1 Earth diameter every second. That's an incredible speed. But you can actually see that. Usually when people measure radial velocities in stars, in spectra, you can hardly see you can't really see the variations in the line very much, especially at this low a dispersion. But here you can really see it happening. You can see how fast the spectrum changed as the envelope exploded, and as the envelope expanded, then you can see, and as it thins out in the outer edges, you can see deeper into the envelope. And that's what you're doing here. You're seeing deeper in and seeing more absorption lines.
So, okay, that's why we're just seeing the blue shifted part here, because we're not looking through.
That's right.
You look to the opposite side.
No, you don't see the other side. The red shifted side is blocked.
Okay.
So you're seeing only the blue shifted side coming towards you. This is another picture of the Tarantula Nebula, showing the magnificent size of that nebula, complexity. Well, this doesn't look like much to some of you, but this is a CCD frame. Actually, it's a combined CCD frames of 3 CCD frames. Ian combined them in the computer, showing the color of the echoes of the supernova explosion. Now, here's the supernova here, the remnant of the supernova, and here are echoes of the supernova explosion. Now, these are actually clouds. These are, if you look at this, if you're looking at this one here, the light is coming straight towards us and comes in a straight line to Earth. Whereas these are clouds in between us and the supernova, and the light is bouncing off of them and then coming straight to the Earth, so it takes a little longer. And in fact, if you take a spectrum of this and of this, you'll find that this spectrum corresponds to the light that left the supernova close to the beginning. And then this spectrum is from the light about a year later, and this spectrum is the light at the present time. Now that's, scientifically, that's an incredibly interesting slide. And it was very difficult to obtain. Good viewing. You needed good technology to be able to combine it later. Well, we've had a long trip, and at the end of the night, of course, you look at the sky to see the sun beginning to appear on the eastern horizon in the mountains there. If I can get a focus. It's really beautiful. It's worth staying up even though you are finished with your night observations. I rarely get to bed before sunrise. And then finally sun makes it up over the horizon. Now just to finish off, that's the end of the travel log. And just that we can have a little bit of light, if you like. Just to summarize some of what I've gone over, Canada we're proposing a new telescope for the Southern Hemisphere. The reason we put that little telescope down in Chile is not because we really want to have a little telescope in Chile, but because we wanted it as a primer. We wanted to show that we could actually operate 6,000 kilometers away, and that we could operate and we could do good science, in fact better science than we can do anywhere else. And we showed that. But then about the time we actually showed that, the budget deficits had already started hitting, and science funding kept going downhill instead of uphill, and we just haven't been able to get a 2-meter telescope down there. But basically, Canada is facility poor, and we depend tremendously on the United States and on the generosity of the United States. They're very generous. NSERC is also struggling. That is the National Agency for Funding Astronomy in Canada, is struggling to try to keep money flowing to the astronomers, but the budget keeps getting cut, and they do the best thing they can do, but they can't keep up with the tide. So it turns out that Canadians, the Canadian astronomy community is really quite talented. It has a lot of good people in it, but we depend on the U.S. to keep us going. UTSO, for example, is the only Canadian telescope in the Southern Hemisphere, and we have something like not 10% of the U.S. power, but 1.2% of the U.S. Southern Telescope power. In fact, this slide was made up a little while ago, and it's now, with the new telescopes being built, it is now about 0.2% of the U.S. telescope power in the Southern Hemisphere. Canada, France, Hawaii telescope and University of Toronto Southern Observatory are the only Canadian telescopes that clear dark sites where the seeing is magnificent. It is where the skies are clear in Chile 85% of the time, in Hawaii about 85% of the time as well. And the seeing, the size of the images is as tiny in Chile as it is anywhere, and is also as tiny in Hawaii as it is anywhere on Earth. Well, we also, I've had some discussion at dinner, we're also positioned for, there's very few permanent jobs in astronomy for talented young Canadian astronomers. We're losing them. They're going to the States, which is okay. I mean, they're getting good jobs, they're doing good work. And as astronomers, we shouldn't really be nationalistic and care about whether they're Canadian or American. We're training good people, they're doing good science. What more can we ask, I guess? But there's also not enough technical support, engineers and technicians. That is, when you cut the budget, that's what you cut out. And so, in fact, which means that good scientists are working inefficiently and doing some of the jobs that a technician can do. Or, in fact, some of the jobs that we work on are things that a third grade student could do. But that's what you do when you don't have money. But the amateurs, I guess, are used to doing everything themselves, so they probably aren't very... You probably aren't very sympathetic. So we've shown basically that we can produce excellent science at an outstanding site with a very small telescope. And it would be a good investment in the future to take the next step to go up to a 2-meter telescope. And basically that comes back to my original argument that we need a balance of telescopes in the southern hemisphere, the northern hemisphere, of sizes of telescopes. We need to have, if we want to do the best science, we have to have a nice balance of telescopes. So with that, I think I've gone long enough, and I'm good for all night, so if you have questions, we can continue this. Thank you very much. Somebody turn on the lights.
Yeah.
Yes.
Would it cost very much to twin the 24-inch? In other words, you've already got the facilities there. You've got the house there. You've got one dome. Would it, in your estimate, by going to some benevolent people or something, a 24-inch telescope, I imagine, is not out of question. It's not something extremely expensive. What would a 24-inch cost you?
A 24-inch of the same quality as the one we have,
Yeah.
Would cost us probably about $300,000 now, something of that order, I would guess, $250,000. Now that telescope actually is a rather special telescope. The company went out of business after it sold it. But it's a rather special telescope in it. It's massively built. We can hang on the end of that 24-inch telescope a 500-pound instrument if we needed to. It's massively built and well built. René Racine also is an optical optician and is very experienced in that. And he, in fact, was the one who tested the mirror, both, well, the secondary and the primary. And he rejected 3 primary mirrors. The company wanted to give him the same old Foucault test and say, well, you know, this is good enough, this is up to your specs and so forth. René said, no, I want to do my own tests. And he took Hartmann masks and a whole bunch of things to really do the tests. And he found that, in fact, the mirror was not up to snuff. And so he rejected it, and then they tried it again, and then there were too many bubbles in the second one, so he rejected that one. So that mirror is actually a superior mirror for a 24-inch telescope. So it probably cost the company much more than it would have otherwise, just to meet our specs. And duplicating the 24-inch telescope, I think, would in fact not wash. I don't think that people would be very interested in it. And we do have the house down there, but the house only has 1.5 bedrooms. So we'd have to build separate dormitories on the side of the house. To build, we have costed out a 2-meter telescope, and we can do a 2-meter telescope anywhere between $2 million and $5 million, depending on whether you want a Cadillac or a Honda. And so 2-meter telescope is actually a workhorse. It's the best sized telescope possible. It's the compromise between being able to go faint and cost. Since the costs go up as the 2.6 power of the aperture, you want to have some balance there. And the best balance is achieved at about 2 meters. Mm-hmm.
What about this, news that we're reading about, like in Sky and Telescope magazine recently, where there's this non-profit organization, I think it's getting started by some English guys with this, setting up a network of, remote sites inexpensively and stuff. Isn't that?
Yeah, that is in fact a great movement, and there is a group which is putting together a very cheap 2-meter telescope, and we're in touch with them. You can actually, when I said that we think that we can build one between 3 and 5 million, a 2-meter telescope, that means that includes site development, auxiliary equipment, and everything. So the telescope would cost, the way they're trying to do it is they're going to try to have the economies of scale, so they'll produce a whole bunch of them, and as a result they'll presumably be cheaper. Yeah, that's a good outfit, but I don't think they've done anything yet, and I haven't heard anything from them for about a year. So I'm a little worried that they either didn't get much response or enough response or something.
I thought they had some level of commitment setting up a half dozen sites, 3 in the north, 3 in the south.
Yeah,
like that.
but as I say, I haven't heard anything from them for a while, and I'm a little worried about that.
Well, there was an article in it, I think it was in the December.
Oh, okay, I haven't seen that one.
Yeah.
Good. That means that they may be still alive. That's great. Now all we need is money. So if you have any banker friends, or I guess the banks are doing real well now, so we need to have some banker friends. Actually, it was interesting. I've tried, one of the problems with raising money at the University of Toronto is that the university administration has to okay you're going out to a certain person or industry for money. And so it takes a couple of years to get their okay. That's the problem. You can't react fast. So I just do a lot of cultivating of Canadian companies operating in Chile, for example. And did you know that the Bank of Nova Scotia actually has bought 30% of the Banco Sudamericano, which is a big bank in South America, and they're going to use that as a jumping off platform for expanding into the rest of South America. Well, that's kind of exciting. So I met actually the ambassador, Canadian ambassador to Chile, invited me to dinner one evening with 24 executives of Canadian companies operating in Chile. Well, I was having fun. So I invited them all to the observatory, of course. None of them make it because it's a long trip from Santiago. But anyway, Richard Joel, who was the director in Chile of the Bank of Nova Scotia, actually did make it to the mountain. Now he's a man about my age, and he wrote me a nice thank you note afterwards. He just fell in love with the place. He was so enthralled with it, and he said, Bob, he said, when I grow up, I want to be an astronomer. So now, actually, just in the last few months, Richard has been transferred and is now vice president of Bank of Nova Scotia and is in Toronto, and I'm going to make an appointment to see him, help him to grow up. Yeah.
How much is astronomical research still the basic stuff, a victim of fashion itself?
Oh, it's always a victim of fashion. I don't know if you all heard the question. The question is, how much is astronomical research a victim of fashion? The fad now, it's always fads. When I was a graduate student, it was about 10 years after they had discovered photoelectric photometry in a big way. And so they thought, well, we can do everything with photoelectric photometry. You don't need spectroscopy. You don't need any of these other things. Everybody and his brother and sister were becoming photoelectric photometrists. So as a result, they were dime a dozen in the late 60s, and they weren't getting jobs even in that rich time. Whereas I decided to go into spectroscopy, and nobody was going into spectroscopy, and so I've never applied for a job. Actually, I have been offered the jobs before I even got to the point of applying for them. So it was the right choice. But photoelectric photometry is now we realize that it doesn't do everything for everybody. It isn't the thing we thought it was. So the current fad, of course, is cosmology. If you want to find out what the fads are, you look at where the students are going at the undergraduate and the graduate level. And at the University of Toronto now, our graduate student population is about 5 per year. We admit 5 new graduate students a year. At the present, so we have about 25 to 30 graduate students at all times. And at the present time, about 90% of those are working on cosmology. So that's the fad. So if I were an astronomer, if I were a graduate student and I wanted to go into astronomy, I would not go into cosmology. Because now what we see at the job interviews at the American Astronomical Society meetings, for example, you see people lined up, and you see that there are not very many jobs being offered in cosmology, but there are 90 times as many people looking for those jobs as there are job openings. Whereas a job like a spectroscopist, there are very few people looking for jobs like that, or with the talent or the skills. So I would go into spectroscopy now too, a stellar spectroscopy even. So there are fads, and a canny graduate student will not follow the fad, because then it's hard to predict what is going to be the fad in 5 or 10 years when you're looking for a job if you're just starting graduate school. So you don't want to start doing what everybody else is doing.
So even the basic research that you're doing, like at the Southern Observatory, how much of that is fad driven? I mean,
not very much. But in fact, I would say that in applying for funding, we have to emphasize the faddish stuff. So clearly, I emphasize the NASA Extragalactic Database, and I emphasize the macho, because those are the popular things, and those are the in things to do these days. So when I'm applying for funding from the federal granting agencies, I know that the people on the committee are going to be looking for faddish kinds of, well, I mean, that's a crass way to put it, but in fact, that's what it boils down to. It's too bad that that's the way it has to go. And I think it's worse now. As the budgets get shorter, people get, you need to hype things more. And so people do hype things more. You see it in all walks of life. It's not just in astronomy. We live in a hyped world. And we don't look at things as rationally as we should in many ways, because you have to sell it. And that's fine. I mean, a certain amount of selling is good. But when that's really what drives you, it's not good. Mm-hmm.
Speaking of stellar spectroscopy, I'm intrigued by this helium star. Could you tell us a little bit more about that?
The pure helium star?
Yeah.
Well, yes, that was part that we were doing a survey of the spectra of hot stars. Okay, and I took this spectrum of this star, and that was back in the old days, 1973, when we were developing of photographs. You know, you ever remember those? And I developed this, and I pulled it out of the fixer, and I thought, gee, I must have tipped the plate upside down in the fixer, because this looks very strange. And then and then about 30 seconds later, I decided I hadn't turned it upside down, and that the lines were indeed very unusual. And the only lines in the spectrum are lines of ionized helium and neutral helium, period. No hydrogen, zero. And that was with a small, low dispersion spectrum that I discovered it. Well, some years later, a theoretician, stellar atmospheres person, did a stellar atmosphere study of a high dispersion spectrum of that same star, And this is Kudrytski at Kiel, and he's probably the best person in stellar atmospheres today. But he and I met at a meeting, and after I showed the slide, he said, you know, Bob, he said, after I got the result of 3 months' work doing stellar atmospheres work, he said, I almost gave up stellar atmospheres because you had in 20 minutes looked at the spectrum of that star and discovered everything about it that I took 3 months to discover by using all the most modern and best theory I could, and high dispersion as well. So that was a spectacular discovery. And it was very satisfying. I mean, it didn't make the cover of Time magazine. It wasn't as spectacular, but it's actually very important because you have to ask, what is that helium star doing there? How did it get there? And in fact, that star is alone in the field. It's not a member of a cluster, but it's hot, it's massive. And it's pure helium. Now, the only thing we know that's pure helium is the core of a red giant star. So somehow that star has blown off its whole envelope cleanly because there's no nebulosity around it, no mass loss around it, nothing. So that didn't quite fit, and it wasn't part of a cluster, so we didn't think that it formed, and it couldn't have formed of pure helium because we don't have clouds of pure helium in the sky. So it's still a puzzle how it got to be what it is. It's there's a lot of fascinating stars up there, and these are bright. I mean, it could be observed with a 24-inch telescope. It's not something. Another thing that was on that list that you may not have seen is the brightest cataclysmic variable known. It still is the brightest one known. It's 9.4 magnitudes, which is easy duck soup even for a good spectrum taken with a small telescope. Whereas most of the cataclysmic variables, these are stars, for those of you who haven't heard the term before, these are stars where you have a hot, very massive star and a cool, small star. And the hot star is pulling material off the cool star. And they're close. It's a close binary. It's pulling material off the cool star and forming an accretion disk around the hot star. And what you see is you don't see the hot star, you don't see the cool star, you see the accretion disk. And it has certain characteristics which are easy to determine from the spectrum, but not easy to determine otherwise. And so anyway, we discovered that most of those types of stars are down around 15th, 16th magnitude, and in order to get a spectrum, you have to have a big telescope. So they were the playground of the big boys, and we little guys couldn't play with them. But now that's why I call that the people's CV, because it's something that everybody can look at. There are a number. I mean, we've done a whole bunch of things that way. That telescope has been enormously productive for the amount of money it's spent on it. Yes.
The cost per paper that you illustrated. I mean, sometimes in talking to some astronomers, everyone has their own take on what is valuable and what is not.
Sure.
And how do you rate that? I mean, you can produce a lot of paper, and you can produce, and all it is just literally paper.
That would be very difficult. The best measure. I mean, if I could do it, I would do it. The best measure would be the published photons. That would be a good figure of merit, the number of published photons, and because you get a lot more photons per dollar with a small telescope than with a big one. But as far as judging the value of papers, it's almost impossible to do because it depends on your bias. If you think that observational cosmology, that is the edges of the universe, are the most important thing we can possibly do, then obviously nothing we do with a small telescope is worth anything. But if you think in terms of the advancement of the science and the understanding of stellar astronomy as well as the understanding of the universe and so forth, then there's just as much good science done with small telescopes as with big. But the key thing is that you have to have a good sight. You have to have good equipment. What we have that most people don't have is good equipment on a small telescope. We have an auto guider. We have a tip-tilt secondary. We were the first to use what we call a tip-tilt secondary for guiding, and that was we were the first to use it for a whole telescope. It was an idea which we got from the high-res camera on the CFHT, but where they actually, in order to keep an image from wandering, you tilt the secondary, and you can tilt it very fast. In fact, we can run it up to about 100 hertz. About 100 times a second we can tilt this with piezoelectric crystals. And it's a fascinating idea. Well, we were the first to put it on actually on a whole telescope, not just on a little camera. And so we guide our telescope with that. So we have an auto guider with that feedback going back and forth. And so the instrumentation we have on that telescope is fantastic.
Is that published name?
No. But it's a common thing now. Now there's several telescopes that have it.
When was that installed?
About 3 years ago. So there are now 2 or 3 other telescopes that have the same thing. The problem is that, you see, with a small telescope we could do that. We've got a small secondary, right? But if you've got a 10-meter telescope, you've got a huge secondary. You can't move it quite so easily. So they couldn't do the same thing. But instrumentation is a key factor. A good sight is a key factor. That's what we've got to our advantage. You don't need a sledgehammer to do a little job, to hit a fly.
What, if any, impact has the Hubble Space Telescope had on ground-based astronomy? It seems like, it's the instrument that sort of caught the public imagination with the spectacular results that are spilled into the media.
It's wonderful. It's a wonderful thing, and it does things that we can never do from the ground. And that's at a cost of about $1.5 billion, of course, for $2 million. So for a telescope that we could we could get for about $1.5 million. But no, the Hubble Space Telescope is of course enables us to look in the ultraviolet. It also gets us smaller images than we can get from the ground. Although CFHT is arguably the best telescope in the world, and Canada wants to mothball it in order to pay for the Gemini, which is not going to be the best telescope in the world. Stupid. But CFHT is a fantastic telescope. It's certainly Racine's baby, and he's done a great job. But what we've done in Chile, the way we operate with Space Telescope is that we coordinate observations with them. So they're observing some object for several nights, and it's a variable object, and they want to know what it's doing. And they're observing it in the ultraviolet, say, and they want to know what it's doing in the visible. So we can easily reach it, and we can in the visible we monitor it for them. So those kinds of coordinated observations we do a lot of with AXF and the Extreme Ultraviolet Explorer satellite and others. We've done, I would say about 5% of our work is coordinated observations.
But the Hubble scope, though, it's, I guess, considered to be a kind of a sexier piece of hardware.
Well, sure. Pay for what you get. Yeah.
But that shouldn't have too much.
No, that's $1.5 billion versus our $100,000. So.
Yeah. Okay, well, it's certainly not very now, just monetarily, but.
No, but it is spectacular. And it is. But before the servicing mission, actually, the Hubble was really hurting for discoveries. They were not discovering things, and they needed a discovery. The service mission did them a great service because it at least produced prettier pictures. Before the service mission, they weren't even getting pretty pictures out of it. But I was there when they showed the first pictures after the service mission, and they were just magnificent. It was great stuff. So the Hubble is a magnificent machine. We just can't afford to. Astronomy is different from other sciences in the sense that we have so many objects to study. there's an endless number of objects to study. We can't just rely on one telescope to look at a few objects. We've got to look at them all. We've got to look at as many as we can. In other words, we've got to for discoveries, we've got to increase this interface between reality and the observers.
But I guess the ones that pull the purse strings for meeting out funds like that, they're the ones that guess that have to see the light.
Well, I'm trying, and in fact, we've done pretty well with the Canadian government. They've given us funds when they have them, and that's the basic problem is higher up than the granting agency. It's not the granting agency; it's one step or two steps higher than that, where somebody figures out the budget. You know, Canada is a member of the Group of Seven. The G7, I guess it's a group of seven, something else, but the G7, and we really don't deserve to be, because in fact the amount of money that we spend on the percentage of our gross national product that we spend on research is much lower than any of the other G7 countries. So the U.S. spends close to 2% of their gross national product, which is large, on research and development. Canada spends something like 0.6. So percentage of GNP even, we're way down the road. And if only we could get a boost in that, I think things would be fine. We have good astronomers. We have excellent astronomers. In fact, I would say that the average Canadian astronomer is better than the average U.S. astronomer by quite a bit. Some of their best astronomers are better than our best, but you know that's a different story. So we have damned good astronomers, and I'm sure in other sciences too. But the support level, there was a study done by Michaud of it, and the support level is about 1/3 per astronomer of that of the U.S. So we're doing very well. We compete well. We publish well. And we have our good share of discoveries and advances, but on a much reduced scale, much reduced budget, not a much reduced scale. So I think we'd do better if we had an equal budget, frankly. But then, who's nationalist? Yes.
Are you still following up on Supernova 1987?
No, we've lost it. It's down below what we can observe, and in fact, we did observe it for about 3 years, and in fact, we had an interesting experiment on our telescope that we had what we call the black box, which would test for millisecond pulses coming from the pulsar. And we did that for 3 years until it just got too faint for us to do. And then they switched it to the 4-meter telescope at Tololo. And that was when they had the false discovery of a pulsar at the bottom of the supernova. And that was produced by some problems with their telescope. So we didn't... Yeah. So it was... Right. So we didn't discover a false image, although we had several interesting false alarms. I remember being running an observatory in Chile is exciting. For example, we just repaired a big problem with the electronics in the readout, the focus readout, by email. You know, test this point and tell me what voltage you get there, and tell me that test this, test that. We finally figured after a week of email back and forth, and we finally were able to correct the problem. That's hard work, but anyway, it's fun, and but there are lots of adventures. I could describe many to you, but. One time, whenever we got a result from this black box, we would put it on tape, send the tape by courier back to Los Alamos in the States, and then they would run it through several crays to look for this tiny possibility of a tiny signal of a pulsar, and then we would want to confirm it. So in fact, every once in a while, we'd get a call from Los Alamos saying, "Quick, we want a confirmation. We think we got maybe something," and of course it would turn out to be noise. But we'd scramble to get the confirmation. Well, this one confirmation when I was down there, I didn't know how to put the black box on, and John Philhaber, the resident, was down in Santiago. He was in the bed of some Swiss miss, I guess. But it was anyway. He was incommunicado, shall we say? So they had serious rains in the south and washed out 2 bridges, and there's only one road in Chile. It's the Pan American Highway. So you wash out 2 bridges, you don't get from A to B. So we got this call saying had to have confirmation. So I had to get to Santiago, find John Philhaber, get him back up to the mountain, get the tape, and then send it to Los Alamos. Well, it turns out there were only 2 5-passenger planes a day flying between La Serena and Santiago, and they were absolutely jam-packed because the roads were out. So I don't know who the secretary had to kill to get space on the plane, but she did get me a seat on the plane, and I went to Santiago, met the next observer coming from Toronto at the airport, and we tried to get him and tried to get in touch with John Philhaber to get them on a plane going back. And we got about 5:30 in the evening, we got word that there were 2 seats on the plane that they, I don't know again what strings they had to pull to get them, but they got them. So, and that they had located John Philhaber, and he was only about 2 blocks from the airport, so he got there. I took the observer by the hand. We ran 2 kilometers across downtown Santiago to the hotel to pick up his bag, took a taxi out to the airport. We got there 2 minutes before the flight took off. He got on the plane. The 2 of them got up to La Serena. Then they went, by midnight they got up to the telescope. They took the tape and sent the observations back to Los Alamos, and it turned out to be a false alarm. So, that's the kind of thing you go through when something exciting comes up, and even if it's just a false alarm.
Maybe we can continue discussions in more informal basis if anybody wants to continue. I think thank you, Dr. Garrison.
So this is astronomy. I think modern day astronomy differs quite a bit from some things. If you're lucky enough, I guess, to get a job in it, then I'm talking to him over dinner. It seems like some people just spend in a nice comfy room eating Oreo cookies, I guess. In the base of a big telescope, if they're so lucky as to get time on it. Some of us in the room are amateur astronomers. I think we relate a great deal to the hardship of trying to observe in wayward places with failing equipment, though admittedly we may not have too many computers. Well, at least in the past we never had too many computers to work with. Now we do have that, and we have a number of people in Ottawa that actually have computerized equipment, and I think they probably have an easier time than the professional, it seems, with equipment failures. At least you just have to go down the road and get a few more components, some active components or Radio Shack or whatever. The talk we've heard tonight has been quite different from the other talks we've tended to have in the past, where we've isolated on one particular topic, whether observing one type of object or enjoying the night sky or meteors. What I enjoyed about the talk was that it was really several rolled in together, showing the human side of astronomy and human side of observing, and even the human side professional astronomy, and if only it could be maintained that way. I personally like small telescopes. You can really grab at them. Big telescopes, you push a few buttons, or in fact I suppose even the astronomers don't push the buttons, somebody else does it. Otherwise you'll drive it into something. It just happened in parks, I believe. Some astronomer drove the dish into the ground and bent it. So you can appreciate the troubles of setting up a small observatory, and goodness me, if there are people in the audience, I suppose, that have that connection with banks and companies, I think it's to fund small telescopes is really the way to go, to have a great deal of impact upon the science. And I think the talk we heard tonight certainly gave you indication as to how it can improve and how you can improve the science by supporting, if not in money, at least talking to your friends to spread the word around. So I'd like you to join with me in thanking the speaker for coming up from Toronto and giving us a very enjoyable talk.
that, I'd like to thank everybody for attending. I hope we see you at the Observers Group meetings in the coming year at our new location, and have a good year.